Hey there. In this video, we're going to do a review of power series. Now, some of the things that we are going to talk about, it should definitely be familiar from Calculus 2, but towards the end, we're going to touch on some things that are maybe new you haven't done in Calculus 2 that we're going to need to be able to do with power series to solve differential equations using them. So first thing, a quick review of what a power series is. It's a summation where I have an x to the n in my series. So for example, here I have the sum from n equals 0 to infinity of Cn times x minus a to the n. So the a is what this power series is centered around. So we would say this is a power series around a or about a. Normally the ones that we're going to work with in this class are going to be centered around 0, but we might run into other ones. So this is what it looks like if it's centered around a and if it's centered around 0. Now, one of the things we were concerned with was when is a power series convergent, because this is the domain for our power series. So it's convergent if the sequence of partial sums converges, or if I take the limit of the partial sums, then that limit would exist. I get something other than infinity, or does not exist. A series is absolutely convergent if I take the absolute value of the series and then prove that that is convergent. If I know that a series is absolutely convergent, then that also implies that it is convergent. So it's like a stronger type of convergence. And just to note, if all the terms of your series are positive, then taking the absolute value doesn't do anything. It's just the same as the series before you took the absolute value. So that would mean that if it's convergent, then it's also absolutely convergent. Now, most of the time we're going to use ratio test or sometimes root test to prove that a power series is convergent. So just to refresh our memories on what the ratio test for convergence is, specifically we're using the absolute value ratio test. And so this is when I take the limit as n approaches infinity of the absolute value of the ratio of successive terms. So a sub n plus 1 over a n. And I'm going to evaluate this limit. And if I get something less than 1, the series converges absolutely. If I get something greater than 1 or I get infinity, then the series diverges. And for the ratio test in general, if the limit is equal to 1, the test is inconclusive. So we don't want to run into that issue. Now, we're going to be doing power series where there's an x in there, so we should never run into that situation. Now, sometimes if the nth term of the series happens to be all raised to the nth power, then I might use the root test instead of the ratio test. And that's just the limit as n approaches infinity of the nth root of the absolute value of an. And then the results for that are the same. If you get something less than 1, it converges absolutely. If you get something greater than 1 or infinity, it diverges. Okay, so interval of convergence for power series. The interval of convergence is the interval of all x values for which the series converges. And the radius of convergence is the radius of that interval, which is going to be the distance from the center to either one of the endpoints of the interval, or half the distance, half the length of the entire interval would be your radius. Okay, so for a power series, we're going to run into one of 3 possibilities for its convergence. The first one is if it's convergent only at A. A power series will always be convergent at A, wherever it's centered around. That's the minimum. And so here, if it's centered at exactly A, it's not really an interval, it's just a point. X equals A is where it's convergent. And that means that the radius of convergence will be 0. The opposite extreme to this is if it's convergent everywhere. And so this would be the interval of convergence is negative infinity to infinity. I got those backwards in my interval, sorry. And then the radius of convergence here would be infinity. The third option is something in between, where I get some finite value for the radius of convergence. And so then the interval will be centered at A, and the endpoints would be R to the right and R to the left to give me my interval of convergence. So visually, it looks something like this, where I have a number line, and I've got my interval is where it converges, and it's the center of that interval will always be A, and then everything outside of that interval is where it diverges. Now, the thing we got to be careful with that makes this last option the longer problem to solve is that the ratio test is only going to tell me that it converges in between these two endpoints. It will not tell me whether the series converges at these endpoints. So both of the endpoints will have to be checked separately to make sure that it converges, or maybe it diverges at one or both of those points. So let's do an example. Here I have a series from n equals 0 to infinity of 5 to the n over n squared times x to the n. So it's a power series because I have the x to the n. And I'm going to do the ratio test on this. Not everything is raised to the nth power, so I don't want to pick the root test. So I'm doing the ratio of successive terms. And so I end up with the limit as n approaches infinity of the absolute value of 5 to the n plus 1 times x to the n plus 1 over n plus 1 squared. And all of that is divided by the original nth term. So divided by 5 to the n times x to the n over n squared. Now make sure you're including that absolute value. It's actually super important. If I don't have an absolute value on this, I won't get 2 endpoints at the end of the problem. Okay, so if I simplify this a little bit, I have a fraction divided by a fraction. That means I flip the bottom one and then multiply them. So the n squared ends up on the top with the 5 to the n plus 1 times x to the n plus 1. And then everything else is on the bottom. So I end up with 5 to the n x to the n times n plus 1 squared in the denominator. And then I can start canceling things. I've got 5 to the n on the top and bottom that'll cancel, and an x to the n that'll cancel as well. So I end up with the limit of the absolute value of 5x n squared over n plus 1 squared. Now, at this point, we got to remember how to solve or evaluate a limit at infinity. It can be helpful, not required, but it can be helpful to take the parts that don't have an n attached to them and pull them out in front of the limit. So that 5x is multiplying by n squared, but it's not stuck in there like the plus 1 is. So I could pull it out in front of the limit. So I have the absolute value of 5x. And then everything else is positive. So the absolute value just stays with the x. It always will stay with that x. And then in the limit, I still have n squared over n plus 1. Now, in Calculus 1 and 2, you probably learned a few different ways of solving something like this. When it's a polynomial over a polynomial, I usually take leading terms to evaluate it, but it's not the only way to do it, and it's fine if you use a different method. But if you take leading terms, the leading term on the top is n squared, because it's the only thing there. On the bottom, if I were to distribute out that n plus 1 squared, the leading term would be n squared. And so I can just simplify it to just that. The plus 1, as we're going to infinity, has little impact on this limit. And so we're basically just dropping out the plus 1. And we end up with n squared over n squared in the limit, which is just 1. So the limit of that is 1. And so my result for this whole limit is the absolute value of 5x. Okay, so I evaluated the limit. And if we remember, the ratio test says, well, this series will only converge when the limit is less than 1. So that is an absolute value inequality that I can create and solve to get my interval of convergence. So now I have to remember how to solve an absolute value inequality. So if there's anything outside of the limit or outside of the absolute value on the left side, you want to move that over first. So if it was like a plus 1 or times 1/2 or something like that, I'd want to move that over to where the 1 is. And I don't have that here, so I can go to the next step, which is to get rid of the absolute value. And so to do that, when it's a less than, which it will always be less than for us, is you take the number on the right side and you replicate it on the left side, only make it negative. So I end up with the compound inequality, -1, less than 5x, less than 1. Okay, so I got rid of the absolute value. The only thing left to do to solve this is to get the x by itself in the middle. So I'm going to divide all 3 parts by 5. And I end up with an interval of convergence of -1/5 less than x less than 1/5. So those are my endpoints for my interval. I can find the radius of convergence at this point. This one's centered at 0, so 1/5 is going to be my radius. But I'll show you at the end how to calculate it if you aren't able to just eyeball it. So next thing we got to do is test these endpoints. So I'm going to take each one of them and plug them into the original series. So -1/5 is an x value, so I'm plugging it in for x, and then I'm going to simplify. It should reduce down to something nicer. If you find that you're not getting matching numbers like the 5s here, then I would double check to make sure you evaluated your limit correctly and solved for the endpoints correctly. So here I've got 5 to the n over n squared times negative 1/5 to the n. So there's a 5 to the n on the top and the bottom of this. So those are actually going to cancel out, and I can simplify this to just negative 1 to the n over n squared. And now this is where we have to remember all of the other convergence tests that you learned in Calculus 2, because any one of them could apply. We usually go for the easier ones like geometric series or p-series, that kind of thing, but you could use any of them that would work here. This one is an alternating series, so I'm going to use the alternating series test. So one of those criteria is that it has to be decreasing. So I do the ratio of successive terms, so a sub n plus 1 over a n. And so that's going to be 1 over n plus 1 squared divided by 1 over n squared. And if I simplify that fraction, I get n squared over n plus 1 squared. Now, n plus 1 squared is always going to be bigger than just n squared. So I can pretty confidently say that this is going to be a proper fraction where the denominator is bigger, which means that it's less than 1. So I've proven the first thing works. The first condition is met for alternating series test. It is decreasing. Second one is just evaluate the limit of the nth term without that alternating piece in there. So 1 over n squared. If I take the limit of that as n approaches infinity, I got to get 0. And I do here. I have a constant over something getting increasingly large. So it's going to approach 0. So it's met both of the criteria for the alternating series test, which means that the series converges. So the endpoint negative 1/5 is included in the interval of convergence. It means I'm going to put a bracket on it when I write my interval instead of parentheses. Now let's test the other endpoint. So now if I plug in 1/5, well, the 5 to the n's cancel completely. I just get 1 over n squared. It's not alternating anymore. In fact, it's a p-series, so I'm going to use the p-series test. Here, p is 2, and whenever the p is greater than 1, then the series converges according to the p-series test. So this one also converges, which means it also, this endpoint is also going to be included in the interval of convergence. And I forgot to put the answers. Okay, sorry. The answer should be, we're supposed to pop up here. So the interval of convergence is negative 1/5 to 1/5 with brackets on them, is what we should see there. And then the radius of convergence, if you add the endpoints and divide by 2, that will give you the middle, or the length of half of it as well. Okay, so moving on to some other things we want to be able to do with power series. Power series is a function of x. Okay, so on top of being able to do things like convergence, we can treat this like a function as well. And the domain of this function is where it converges. So where it's whatever its interval of convergence is. Now, if the radius of convergence is greater than 0, so it converges at more than just its center, then the function, this power series function, is going to be continuous. It's going to be differentiable, and it's going to be integrable. So I can take the derivative, I can find the integral of a power series as long as its radius of convergence is greater than 0. So for example, let's say I have a function f of x equals the sum of from n equals 0 to infinity of cn times x to the n. I could take the derivative of this. And remember that we're taking the derivative with respect to x. So even though I have n's in there, that's not my variable. Those are numbers, not a variable. So the derivative would be, if I just use the power rule, so derivative of x to the n would be n times x to the n minus 1. Now, I wrote out the first few terms of these series to show why the starting value changed. I started out with a series that was at n equals 0. And because our first term was c sub 0, and then plus c1x, and so on. But when I took the derivative of that c0, well, I get 0. So that term is gone, which means that the first term in the derivative is going to be c1. So now my series starts at n equals 1 instead of n equals 0. So be careful with that. You tend to lose terms when you're taking derivatives. And you might gain terms when you integrate. Right? So really pay attention to the starting value. It helps to just write out the first couple of terms to make sure that you're starting at the right spot. Some other properties. If the radius of convergence is greater than 0, then if the sum of the power series equals 0, then that means all of the coefficients, the cn's, are equal to 0 as well. and that's called identity property. Some other skills that we need is series addition. I'm going to need to be able to take two separate series and write them as a single one. And so we can do that as long as they have the same starting initial value. So if one starts at n equals 1, the other one needs to start at the same value for me to be able to combine them into one sigma notation. So for instance, here they're both starting at n equals 1. I have a sub n times x to the n and b sub n times x to the n. And so I can just write them as a single series, and I can even factor out the x to the n. So I get the quantity an plus bn times x to the n. I can also shift the initial value. So if I wanted to combine two, but they didn't start at the same value, well, I can change those by doing some shifting around. So if I add to the starting value, so let's say it started at 0, I want it to start at 1. Well, then I'm going to subtract the same amount that I added to all the n's in the expression. So here I started out with a series that started at 0, and my expression was cn x to the n. And when I shifted it to start at 1, now I'm going to subtract 1 from all the n's. So now it starts at c sub n minus 1 times x to the n minus 1. So that's how you can shift things and move them earlier. Or sorry, have them start at a later value. I can even change the index as well. Let's say I don't even want them to be n's anymore and I want to change it to something else. Well, you can do a substitution. So here's an example. I have a series where it's n equals 1, and my nth term is c sub n plus 3 times x to the n plus 3. Well, let's say I need that to be just x to one letter and not the n plus 3. Well, I can just substitute it out. So let's say I'll call that n plus 3k and then swap out the n plus 3's for k. So now I end up with ck times x to the k. Just note that changed the index as well. Now instead of starting at n equals 1, k is going to be k equals something. And well, if it started at n equals 1 and k equals n plus 1, or n plus 3, then the new starting value will be 1 plus 3. So k equals 4. So that's how you can shift the index. And let's do some playing around with some of these properties that we were talking about. So here we have a function, f of x, or we actually have the same one that we worked in the first example. So 5 to the n over n squared times x to the n. Let's find its first two derivatives. And then we're going to adjust the second derivative so that it starts at 0. Okay, so for the first derivative, just doing power rule, 5 to the n over n squared is a constant. It's a number. So it does not change when I take the derivative. It's just the x that changes. So I do power rule. I've got n times x to the n minus 1. And now I've lost the first term, so it starts at n equals 0. Or sorry, n equals 1. Okay, and then the second derivative, again, I'm just taking the derivative of that x. So now I take the power rule again, so the n minus 1 gets multiplied out front by the n, and the new exponent is n minus 2. And I also lose another term, so now this one starts at n equals 2. Right, and so now the last piece of the instructions were to rewrite the second derivative so it starts at n equals 0. Okay, so I'm going to change that n equals 2 to n equals 0. And then that means I'm going to make some adjustments. So n is getting replaced with n plus 2. And so I end up with everything changes. So I have 5 to the n plus 2 over n plus 2 squared times n plus 2 times n plus 1, all times x to the n. Okay, so it maybe doesn't look nicer, but if I really needed, the x to be x to the n and not x to the n minus 2, then that could be kind of important. Okay, so the last thing I want to briefly mention before we go in this video is power series representations of functions. So Taylor series is going to pop up here and there. So just remember that a Taylor series formula can be used to take any function and write it in series notation if we need it to be. And we say that a function is analytic at A if the Taylor series at x equal A has a radius of convergence greater than 0. And just for reference, here are some common power series representations of functions. So for instance, e to the x is equal to the sum as n, or from n equals 0 to infinity of x to the n over n factorial. So just a nice reference if we need to be able to switch or take a function and write it in series notation.